One of the things I think, if you're engaged in science at all, is that you do think about discovery. Everybody wants to make a discovery. Everybody wants to have that light bulb in their head. And in fact, when the Cambridge Philosophical Society decided to have an exhibition about its 200th anniversary, some of you may have seen it, some of you may have even put it on, that exhibition was entitled Discovery. And something struck me quite strongly at that point was that scientists are actually really good at thinking about how to organize their labs, the way in which they do their science, the kinds of observational and experimental techniques to adopt, all the kinds of things that go with that. So one of the things that struck me was very much that if you're engaged in science, you actually have quite a good understanding of how science works day to day. In other words, you have quite an on-the-ground feeling about what discovery is. But what also strikes me is that many times scientists don't have that good an idea about how to think about discovery over any longer period in the past. In other words, scientists are thinking about discovery in the future, and they have a model for that, and they're quite good at thinking of that. But in terms of how they think about it, in terms of the whole history of their subject, it gets to be quite problematic. And one of the things I really liked about the exhibition we put on is it actually seemed to me that it did both things. And that wasn't just because I was partly involved in it. I think that it shows that there's a real possibility for scientists to understand the past and indeed help it to figure out how it might inform the work that they're doing today. So I want to inquire a little bit more into the basic notion of discovery. And in order to do that, I want to look especially at the problem of Eureka. Because Eureka, I think, is at the heart of the issues about what goes wrong when people think about how science actually works in terms of discovery. So these are the different sections of the talk. I'm first of all just going to outline what the Eureka Model is. Then I'm going to talk a little bit about what the underlying actual story of Eureka is. I'm going to talk about the transformation of science in the 19th century, because the 19th century in some ways I think is the crucial period when the notion of discovery we have came into being. I'm going to talk about the alternative model, which I think in fact underlay much of what was in that exhibition, and indeed it underlies also the Darwin exhibition, which Claire mentioned, which is on at the University Library. That's my plug. It's only on until the 3rd of December, so make sure to go if you haven't been. There's all sorts of really great things to see. And then finally, I'm going to be talking about Darwin and Discovery, partly to tie in with the exhibition and partly because I think it's a particularly interesting example of how to think about the Eureka problem. So this, I think, chart from the American Association for the Advancement of Science really nicely illustrates how the past of science is often thought about when you think about what science. It's thought in terms of individual milestones. In other words, these are the moments that really matter in science, and the rest of it is just kind of working things along. And when Thomas Kuhn published his famous book on the structure of scientific revolutions, this in some sense meant that, of course, you have periods of what he called normal science, and then you had revolutionary discoveries that really changed things. Now, there might be small-scale discoveries too, but to be honest, many people thought that didn't sound that great. Who wants to be doing normal? So, in fact, underlying this again is this Eureka Model. And here's, I think, a really good example of it. It's when Isaac Newton is supposedly hit on the head by an apple. And you can see a few features of this. For one thing, discovery is seen as very sudden. It happens in a moment. It's instantaneous. It's typically made by a single person, and it's typically made by a person who's a genius. And more broadly, within the way we think about it, it's often seen to be a peculiar feature of reason in the West. These features are evident in little extracts from this American Association for the Advancement of Science diagram. You can see here, for example, Newton discovers universal gravitation, Charles Darwin discovers evolution by natural selection, Albert Einstein, special relativity, and you could go on and on. This is very much the way I think most people think about the way that science works. if you press them, they're obviously going to say a lot more sophisticated things, but there's a kind of core idea of the great discoveries punctuating the way that science is actually developed. And it shows up here. This is one of my favorite examples of this. This is from an article in 1999 about it was at the time that the genome was being revealed. And you can see here, for example, various people. You have Watson and Crick discovering DNA, which of course they didn't do. In the 1750s, you've got a man called Linnaeus who's discovering the principles of taxonomy. So beyond the fact that it's actually rather garbled, all of this, there's a kind of way in which it also illustrates this key moments idea within science. And this is very much the kind of idea that's behind the Eureka model. Now, Eureka, of course, refers back famously to Archimedes. Archimedes was a Greek engineer and mathematician, and famously, he was asked by the king to determine whether the gold in a crown that he had was actually, real gold. Was it actually completely all what it was supposed to be? And he realized, while he was in the bath, that by displacing the crown, he could figure out how much displacement occurred, and that way he could figure out ultimately, by weighing the crown and comparing it with its volume, he could work out the specific gravity. Eureka is the idea. Now, Archimedes famously wrote a manuscript which actually just came up on the market fairly recently, which says, actually, the proofs that we give, that we tell the public, are things that are actually not actually what happens behind the scenes. We need to work out these things, and then we present the completed, say, mathematical proof or experimental proof. And Archimedes wasn't lying in doing that. He was just presenting a streamlined view. Now, this account, as we'll see, doesn't fit very well with what actually happened, or at least what the evidence for what happened. But it means that Eureka for us has become a kind of symbol of what discovering in science and technology actually means. And here again, you have the American Academy of Science chart, where you have Archimedes not only discovering something about the specific gravity of a crown, but how theory can lead to technological insight, which is a pretty big thing to discover in a bath. So this has led, if we look, as I said, to the popular way that people often think about this, is just a small selection of the books like my lecture that are called Eureka. And many of you probably came to this lecture because it was called Eureka. You thought, wow, that sounds really exciting, and it's something to draw you in. And that's why the word is used here. That's why I used it in my lecture. Now, this lecture is really going to try and look at discovery by thinking about the word Eureka and what it actually means. But to do that, first of all, I think we need to step back a bit and look at why the 19th century is a particularly important point in a lot of what we're going to be talking about. And in particular, if we go back here, it's really the theory leading to technological insight. Technology is actually a late 19th, early 20th century word. It's a word that becomes much more common then, and the idea of science-based technology really comes out of that. What we need to do is to look at the period when science became really important for everyday life for most people. Not just something that was, say, important philosophically or in theology terms or other things like that, but something that really began to change people's daily lives. So to understand that, we can think about the transformation of science in the 1800s. And there's a variety of ways in which this actually happens. First of all, I'm sorry, it's going dark again, but we have the Industrial Revolution and the rise of European empires. These are huge changes that really mean the world is much more connected than it had been before, and it's also connected in many ways increasingly by the inventions of science, the railways, the telegraph, the postal system, and other things like that. Another issue, if we can, I'll just try and deal with it now, is new disciplines. This is a period when science itself really begins to change dramatically. It's when new subjects like physics becomes something really important. It's not that people hadn't studied the natural philosophy of what they saw as the created world before that, but in this period, mathematics and experiment come together in new sorts of ways. Geology is a new science, and it's used to explore the resources of new empires. And accompanying this are changing places for laboratories, hospitals, and museums. So in fact, it's no surprise that the Cambridge Philosophical Society was founded in 1819. It's right on the cusp of these new developments coming in. So the other thing that happens is that new roles for the scientist actually develop. If you take all of you in this room, this probably around, say, I don't know, 1650, would have represented the number of people who are actually really keen on daily work in working on science, people like Galileo or Newton and so forth. It's not a huge number of people. Whereas now, that's how many you get in a large undergraduate lecture at one institution. So the scale of science really changes. And this scale change begins in a big way in the 19th century. It's a period when the word scientist is invented, and then really by the end of the 19th century is being regularly used. And although there had been scientific news before this, this is a period when the scientific article and scientific journals really get invented. So science becomes much more important, as I said, for daily life, for the nation, for the empire, and for the economy. And this is across Europe. It's seen to be something that's really, really crucial for the development of the imperial nation state. Now, how does this affect the development of discovery and notions of discovery? Well, for one thing, science becomes much more tied to the pulse of daily life. Science becomes effectively news. It becomes something that's reported in the newspapers, and the scientific article is much more focused on an individual, specific discovery. That's typically what scientific articles start to do. They become much less wide-ranging, less dealing with many different subjects. They become focused, and there's the idea that it really matters when things happen is something that's introduced. I was outlining just how important the changes in the 19th century are. And the crucial thing here is that this provided something where, because science became more relevant and important for daily life, it also becomes something where the timing of it becomes really important. So one way of thinking about it is discoveries in science become more like scoops in newspapers. And a really good example of this is in Nature, which was originally founded, it's a weekly, of course, and think about what that means. I mean, that means every week new science matters. So it's something where those timings really start to matter a lot. It's not that priority hadn't mattered before then, but it starts to matter much more than it had. And originally when Nature is published, it's actually halfway between a popular publication and a scientific one as we know it now. So it shows how the most basic ways we think about announcing new scientific findings are being put into the popular press, and also into the scientific press. The two work back and forth. So what I want to suggest now is that understanding this about the 19th century and about this new idea about the way that science works as news is something that is helpful for us to understand how discovery actually changes. And for that, I want to turn back to the story of Eureka. Now, I've already explained a little bit about the ancient Greek story of Archimedes in his bath. This picture, of course, isn't from ancient Greece. This is a Renaissance picture. And in fact, they were drawing on writers after, about 200 years, in fact, after the story about Archimedes. That's when the first evidence for it exists, from other Greek writers like Vitruvius and Plutarch. So this story, actually, think about how long, 200 years is quite a long time. So to be honest, the story may well be garbled from the way it originally occurred, and it almost certainly is. But the interesting thing, I think, is what happens to it. It becomes something which isn't really taken that seriously. And a perfect example of that is that of Isaac Newton. Here you've got Newton's assistant in a letter, writing to a letter after Newton had died, saying, Newton turned himself about, ran up the stairs like another Archimedes with an Eureka, failing to write on his desk standing, without giving himself the leisure to draw a chair to sit down on. So you have this idea, this eccentric person, this geek, really, who's doing these kind of things. Now, there are occasionally more serious examples. This is when Gauss is discovering a very important mathematical formula, and in his notes, he writes the word, as you can see it up there by the blue arrow, the word Eureka. But this is very unusual to find in anybody's notebooks. And I think there's a certain sort of way in which he's kind of thinking about himself as another Archimedes when he's doing it. Much more common is this kind of view. And this is from a dictionary, quite interesting, which basically says, sorry, you can't read it all there, but it says, Eureka, it is now used mostly in ridicule to mark an affected importance to an insignificant discovery. And here you can see in Punch from 1851, somebody who's supposedly discovering this. And the Roman soldier, as it is, looks rather puzzled by the whole thing. So it's all kind of mixed up in terms of time and place. So by the early 19th century, you have this idea of Eureka as this rather silly sort of thing. But this does begin to change. And if you see how it happens, it's quite striking. And it has to do with this. This is the discovery of gold in California. This is the famous Sutter's Mill, where gold was first discovered. And what you might think somebody would do, the story would be that Sutter ran out and says, Eureka, I found gold. Well, he doesn't say that, in fact. He just does what a normal 1849 person would do. He's really thrilled to discover gold, and it starts the gold rush. How then does Eureka become connected with any of the story here? Well, to understand that, you need to look at this. And this is the man, Robert Selden Garnett, who was in the United States Army. He later on joined the Confederacy. But at the time of 1849, he was working in California. And he is the person who designed the California Great Seal in 1849. And he put at the top, Eureka. And he decided that this would be a good state model for California because of the discovery of gold in relationship to Archimedes. Now, Selden himself, Selden Garnett, was interesting partly because he actually had been trained in the East Coast in a military academy where Archimedes was kind of like the local hero. So he goes there as an Archimedes kind of fan, decides in California he's going to put this on the seal. And this is the tiny link in some ways that then means that gold and Eureka and discovery all come together. And this, of course, is really good news for the word Eureka. If you make a graph just of its use in a Google Ngram, you can see it just zooms up after the late 1840s. You still get some of those comic uses. The one from Punch was 1851, but quite quickly after that, it really changes. It's suddenly linked with the whole idea of gold. And you can see that in the huge range of commercial products that are advertised using the word Eureka in the second half of the 19th century. So Eureka becomes the symbol of science-based technology discovered through this fantastic idea that you're striking gold. And it's similarly, if you look at the discovery of gold itself, you could make a map that showed all the towns called Eureka in Australia, of course, in other parts of the United States, in Alaska, in South Africa. There are many, many places and mines called Eureka. So Eureka suddenly gets this really positive idea about what it represents. And it becomes a symbol in some ways of the new basis on which science, through technology, is changing the world. And it even becomes something that's very important for the understanding the psychology of science. This is a book by a Frenchman named Ribot, where it's basically really about, fundamentally, Eureka moments as the primary motor of the way that science actually operates. So science goes through these moments where people have these sudden insights. That's the psychology on which the whole field works. And that's ultimately how you get, in a kind of quite simple form, this American Academy of Sciences chart. That sort of idea that the whole history of science is a series of great discoveries that we put together. And it's made by these Newton, Galileo, Copernicus, et cetera, Darwin-like figures, and they're all linked together. So what kind of alternative can we have to that? And this is the one, as I've said, I think we tried to show in many ways in the Discovery exhibition. First of all, one thing that's very clear is that discovery is always collaborative. no matter how individual a person is, they're always thinking in relationship to other people. Otherwise, it wouldn't be a discovery. It couldn't be new unless you knew what was old. And you have to also be working quite closely at the edge of where other people are at. So discovery is always a collaborative process. The second thing, and this is rather obvious, I think, but just making a single discovery, just having an idea, is almost never enough. In fact, I can't think of an instance where it's enough. It's always going to be combined with a range of issues, understanding what the longer traditions are, and deep and patient work. And I think you can see that really clearly in, like I said, in the work that was done in the exhibition. But it's also, I think, characteristic of if you think about the way that just ordinary lab work or field work operates. And this is, I think, quite an interesting point. Individual discovery is always a retrospective attribution. It's only when looking back, sometimes fairly quickly back, that you realize that a discovery has been made. And typically, the main discoveries that we think about are only kind of socially validated over considerable periods of time. Their significance really comes out. That's what makes a discovery really important, as opposed to something that just, one step along a range of other things that are happening. So the idea of these sudden, instantaneous eureka moments is something that's effectively a historical construction that we're making when we talk about what we're doing. And then finally, discovery not only is collaborative, but it's also the product of international exchange and cross-cultural encounter. Having people who are educated in different places, having people who are actually coming from different kinds of cultural traditions has always been really important for the making of science. And it's one of the reasons why currently people are worried about the relationship of British science to European funding, precisely because having that infusion of that. And this is true in the past as well, perhaps even more so. So a good example here is to go back to Newton. On the one hand, we have the picture of Newton and his apple, but on the other hand, we have this wonderful picture that my colleague Simon Schaffer put together, which shows where all the information and all the kinds of material that goes in to make the Principia comes from across the globe. And there's some sort of space in between these two pictures that probably tells the truth, although the apple, I'm not really sure, is very much part of the story. But it's really important to recognize just how much this kind of, even a book as old and as famous as the Principia and is out of someone like Newton, doesn't just come out of his head, it comes out of this kind of much wider sort of range of experience. And to understand this, I think one thing historians like to think about is different scales of activity. When we're talking about the kind of chart of key events, we're really talking about something that is kind of history of the moment. It's something that has names attached to it. It's about individuals. It's about short-term things. But in fact, what we need to do, and that's why I tried to outline about the 19th century and its significance, we need to think about the much longer social and economic and cultural history. And ultimately, that's linked into a geographical and environmental history. And Brodel, the famous French historian, says this very well in the quote up there. So what I want you to do in the final section of the talk is really talk a little bit about Darwin, because obviously with the Darwin exhibition and the Darwin Correspondence Project completing its 30th volume, it's a good chance to think about these questions. This picture here is from the 200th anniversary of the publication of The Origin of Species. It was the official UK logo. And I think it is absolutely terrible. It replaces, for one thing, the light bulb with a lightning bolt, which is actually more instantaneous and even. It shows Darwin with a beard as an old man, so he's, it's not in the period when he was actually really doing the work. And more than that, it shows him as a silhouette. So he's kind of like, it's almost like he's some sort of cosmic genius rather than anything that we can identify with. So I think this sent out exactly the wrong messages about what Darwin and understanding Darwin could actually be about. It's sort of the antithesis of what we were trying to do in the exhibition in the university library. And there are different ways in which this works. One way of thinking about that moment of lightning genius is that Darwin saw the finches on the Galapagos Islands, And, you know, this fantastic, beautiful tropical island. The idea is he's all by himself there. And hey, presto, he comes up with the idea of natural selection. That's how the different beaks of the finch work. Well, actually, it doesn't work like that. When Frank Selloway, a historian of science, went to the Natural History Museum and looked at the finches, he realized Darwin hadn't collected them according to which island they were on at all. And many of the birds he didn't even think were finches at all. And so, in fact, it was only later that this all happens. Darwin isn't thinking about finches. In fact, he's not really thinking about evolution, or transmutation as it was called, when he's on the Galapagos. He's thinking about questions about the relationship of new species, or how forms come into being in relationship to, say, South America as opposed to an island. It's about geographical distribution. It's about fossils in relationship to what's currently on the surface, things like that. But he's not thinking about, you know, a kind of evolutionary ideas. It's really only when he gets back and he's in London that he thinks about these. He moves in after he's sorted some of his specimens and stuff. In 1836, he moves to Great Marlborough Street in London. You can see it's right in the heart of London. It's quite near Carnaby Street and Liberties, if you happen to go there. And in fact, this is where, this isn't the original building, that's been long gone, but number 41 here is the place where Darwin discovered natural selection. So what I'd suggest next time, if you think about going to the Galapagos and flying and using lots of petrol and so forth, don't do that. Just take the train, go down to London, have a nice Wagamama meal, and think about the fact that Darwin discovered natural selection only a few feet away from you. Now, this has a really important message for us about the way that we think about what discovery actually means. But if Darwin's working there and thinking through his ideas, that is where he makes the great discovery in 1838. Does that mean, as indeed this book says, it's quite a good book actually, a children's book, it's part of a series called Eureka Moment, and what it says is that Darwin has his Eureka Moment when he's on Great Marlborough Street, when he reads Malthus. That's the moment at which it happens. So are we just exchanging kind of a pastoral, one beautiful tropical island for a kind of grubby but expensive part of London? I think that's a problem too. So we need to think now about how to think about what Darwin's actually doing. One way to think about it, and this is quite important, I think, is that having the idea was just the first step. It was, if Darwin had come out and said, and he knew this perfectly well, if he had come out in 1838 and said, hey, I've got this great idea about how species evolve, he would have been in huge trouble. And it's very clear in his correspondence that he's very careful about how he tells people what he's thinking. And it's not just because everyone's, you know, all concerned with religion or something. It's because they want to keep to good scientific standards. And he's dealing with an idea that really, for the most part, is outside science. So, in fact, what he needed to do was a huge amount of work. And at the Darwin Correspondence, the team there has been editing the letters that really, in some sense, show all the work that went into making Darwin's theory into something that was really secure. And that's his study up there that shows just how he was poised to think through all these questions. But more than that, I think let's look at very specifically at what Darwin's doing when he's on that place in Great Marlborough Street. These are, of course, his famous notebooks, which are now on display in the exhibition. And let's think, first of all, about this page from Notebook B. This is, of course, the famous Tree of Life diagram. Now, a lot of people think this is the Eureka moment in which Darwin discovered his great theory. But in fact, it is a really wonderful diagram, and it says something really interesting. But what it actually says, I think, is that Darwin's trying out a whole range of different ideas. Because the basic idea of this diagram is not to show that plants and animals, the changes in them, it's like a tree. That's kind of, once you start thinking about evolution, it's sort of obvious that that's going to be the case. What he's trying to do here is to show that the number of species that go extinct is roughly going to be equal to the number that come into being. So in other words, there's a balance between extinction and the coming into being of new species. Now, we don't believe that that's the case. This is actually not a theory. This diagram represents a theory that Darwin and we basically, in the end, rejected. But what's great about it is that it shows Darwin thinking through the consequences of his ideas at an early stage. The theory that he's got at this point isn't natural selection, what he became famous for. It's a theory about reproduction, in which the evolution of new species is more or less like the way in which a baby grows up into being a full-grown adult. It's a different kind of theory. This page is actually really the crucial page. This is the page on which Darwin reads Thomas Malthus's Principles of Population, and he describes what's happening as a kind of fierce wedging that's going on, where the strongest and the sharpest and the best wedges are the ones that are going to make it, and the rest of them are not going to get into the face of nature, as he calls it. So it's a very powerful moment within Darwin's work. But the point that the notebooks really make here, I think, and including the Malthus page, is that it isn't just this unique moment that makes it. It's the whole process of moving through these things. Even the way he's writing it there is a process that he's going through. It's not just a sudden moment of realization. Now, it certainly is true that science isn't just kind of one long plane where nothing really changes. This is clearly a very important inflection moment for Darwin's thought. But it's an inflection moment on a constant curve of development, thought, and work that continued right on till the end of his life. So let's think about a few conclusions here. First of all, as I've stressed, I think there is a picture, and I think it's very generally present within the public at large, but I think it's also present within the scientific community, that individual sudden discoveries are really what matter. And one of my favorite examples is this new program from Disney Junior called Eureka, where Eureka invented the wheel. That's very nice. You can see her main use of it is to make the skateboard, which makes all her friends really happy. She has a pet mammoth that she helps through one of her inventions. I don't want to kind of go down too hard on a children's cartoon, but it's actually quite interesting. I think you have to watch the individual programs to see it is actually more than that. But there is a kind of way in which Eureka comes across in a way that's, she seems like different from all the other kids. And she has all these ideas all the time. And you kind of feel like, well, maybe I could be like that, but maybe Eureka is kind of like somebody really different. And there's quite a lot of work in the psychology of modern science that argues that educating students to say, you have to be a genius or you need to make great discoveries, it leads to disappointment for students. They don't understand the range of work that's actually needed and what's actually involved. And so this program's actually successful insofar as it shows, and she does so, Eureka's continually showing it. I've watched more episodes of this than I care to say. Eureka is actually very much somebody who's trying to show the others that, you've got to be careful, don't try to go too fast, you've got to move things in the right way, and you've also got to be able to sing, which is a crucial thing, which, to be honest, I'm not sure is vital for the being in science. So let's look at the image we started off with here, the image of the light bulb in the head. This, in some sense, sort of symbolizes, in many ways, the Eureka idea for a modern audience. And in fact, I think it's a really helpful way of thinking about how we might revise our ideas about what it makes to make a scientific discovery. Here's Thomas Edison looking at one of the very first light bulbs he ever made. He's a little older here, and he's kind of reflecting in precisely this retrospective way about himself as the inventor of the light bulb. If you look at the histories of the light bulb, it's much, much more complicated than that, with all sorts of different people involved and all sorts of different things that are required for it to happen in the first place. So this is very much that heroic, retrospective, genius-oriented picture. What we actually can do instead, though, is look at things like the sequence of light bulbs that mean that we get towards where we are now, and all the different range of things that were present and that have made it into what we actually see. So when we see the picture of the light bulb here, I think it's much better to think about that's a 19th century invention, and this is a very particular way of thinking about how we can think about what the discovery actually represents. And I just want to finally end, which this is one of my favorite quotes. It's attributed to the science author Isaac Asimov. He says the most exciting phrase in science, the one that heralds new discoveries, is not Eureka. I found it, but that's funny. Thanks.